Hello everyone, we are at the topic of diodes. We are looking at waveform shaping circuits using diodes, and in today's lecture we are going to study clamp circuits and peak detector circuits. Here is our ideal peak detector circuit. It consists of a diode that is connected to a capacitor, and the output is taken at two terminals of the capacitor. As the name implies, this circuit detects the peak value of the input signal. When the input signal reaches its peak value, the output is going to be almost equal to the peak value of the input signal, and it's going to stay constant even when Vi goes below its peak value. So V out is almost equal to peak value. In fact, it's V peak, the peak value of Vi minus Vd naught volts. Let's analyze this circuit. First, let's take a look at the case when the diode is off. We're going to assume that the initial voltage across the capacitor is equal to 0. So labeling the voltage across the diode Vd and Id. Considering this node as a reference node, this is Vc, this node is equal to Vi. So Vd is Vi minus Vc, which is initially equal to Vc is equal to 0, so Vd is equal to Vi. From there, when the diode is off, I know that Id is equal to 0 and Vd is less than Vd0. Because Vd and Vi are equal, that means Vi is less than Vd naught. So for Vi values less than Vd naught volts, the diode is going to be off, and we can replace it with an open circuit. So V out is equal to Vc, which is equal to 0 initially. So for this time range, as you can see, the diode is off and V out in this range is equal to 0. I'm plotting V out of t as a function of time with blue color. When Vi increases from Vd naught volts, the diode is going to turn on. I can replace the diode with its circuit model when it's on, which is a constant voltage drop model. And I'm going to write Vd is equal to Vd0. This is plus minus Vd. And Id is going to be greater than or equal to 0 for the diode being on. Now the diode is on and conducts, so Vi is going to charge the capacitor. As a result, V out, which is equal to Vc, is going to increase. Using the KVL, I know that V out equals to negative Vd plus Vi. Because Vd is a constant value, I have negative Vd naught plus Vi. V out is slightly less than Vi. This is the equation for V out in this area. Also in this area, Id is equal to IC, and that is equal to C dVc over dt. This is IC, and that is equal to C dVi minus Vd0 divided by V dt. That is equal to C dVi over dt. Now at this time point that I'm going to label as T sub a, at t equal to T sub a, I have Vi equal to its peak value, V peak, and Vc equals to V peak minus Vd sub 0. From there, because Vd is equal to Vi minus V sub c, capacitor voltage, I'm going to write it as Vi minus V peak minus Vd sub 0. So after t equal to Ta, for other time points, the amplitude of Vi goes below V peak value. So this one goes below V peak value. As a result, Vd is going to be less than Vd naught. As a result, the diode does not conduct anymore because Vd is less than Vd naught. From there, I know that for all of these time points, V out or Vc is going to stay at a constant value equal to V peak minus Vd sub 0. So for all of these time points, the amplitude of Vi is less than its peak value. As a result, Vi minus Vc is less than Vd naught. When Vi reaches its peak value, the diode might momentarily turn on, but for the ideal cases, we're going to assume that the diode does not turn on anymore, because immediately after this time point, the amplitude of Vi decreases from its peak value. So as you can see in this graph, after Vi reached its peak value at this time point, the output is going to be at a constant value equal to V peak minus voltage drop across the diode. So this circuit detects the peak value of the input signal, and after Vi reached its peak value, the value of output is going to stay at a constant value. If you have a time varying input signal whose peak value changes over time, this circuit can be used to detect the largest peak value of the Vi signal. So as you can see, when the first peak comes, V out is going to be equal to that peak value minus VD naught. The next peak is larger than the previous one, so the value of output voltage is going to increase to that peak, to the second peak value minus VD naught point. The third peak comes, and that's greater than the second peak, and V out is going to be equal to the value of the third peak minus VD naught. The fourth peak, here this peak is less than the third peak, but the value of V out does not change because the diode cannot turn on anymore. In an ideal peak detector circuit, there is no resistive path for the voltage across the capacitor to discharge through when the diode is off. So when the diode turns off, the voltage across the capacitor stays at a constant value equal to V peak minus VD naught. Here is the circuit for a practical peak detector. As you can see in this circuit, there is a resistor in parallel with the capacitor. So when the capacitor is charged and the diode turns off, the voltage across the capacitor is going to decrease because the capacitor is going to discharge through this resistor. So for these time points, the diode is off, but the voltage across the capacitor does not stay at a constant value. Rather, its voltage is going to exponentially decrease. And then when the amplitude of Vi reaches a value that is greater than Vc plus Vd naught, then the diode is going to turn on and the voltage across the capacitor is going to increase because diode conducts and the capacitor charges some more, and again it turns off, and then again the capacitor discharges through this resistor. Using the KVL equation in the main circuit and the voltage equation of a discharging capacitor, we can find the output at any time point. We also can find the time point at which the diode turns back on. This is the voltage across the capacitor when it is discharging, and I know that from the KVL, I know that Vd is Vi minus Vc. When the diode is off, Vd is less than Vd naught, so Vi in all of these time intervals, Vi is less than Vct plus Vd naught. Also, when the diode turns back on in this time point, I know that Vd is equal to Vd naught and Id is greater than 0. So I can find the equation of V out when the diode is on. So this is a simple equation because the diode is on. I can replace it with constant voltage drop model. KVL tells me that this KVL in the main loop tells me that V out equals to Vi minus Vd naught. So I have the equation for this section of the graph. The shape of the output signal in a peak detector circuit depends on the ratio of its time constant to the period of the input signal. So tau is the time constant of the peak detector circuit, and T is the period of the input signal. In an ideal peak detector circuit, the value of resistor in parallel with the capacitor is infinity. So tau, which is equal to R times C, and this is R, and this is the capacitor for our peak detector circuit. This is our diode model when it is off, and this is my Vi, and this is V out or Vc. So time constant is equal to Rc. For an ideal case, resistor value is equal to infinity. As a result, tau over T goes to infinity. In practical cases, there is always a resistive path for the capacitor to discharge when the diode is off. But in a good peak detector circuit, the ratio of time constant to the period of the input signal is much greater than 1, and if it is much greater than 1, then the capacitor cannot discharge a lot before the next peak of the input signal arrives. So the output almost maintains its shape. So when RC is much greater than the period of the input signal, the output is going to be almost equal to the peak value of VI. But for example, for this one, the capacitor is going to discharge for values of VI less than its peak value. So it totally discharges and V out is not equal to peak value of VI anymore. The second diode waveform shaping circuit that we're going to study today is a clamp circuit. Now in terms of circuit configuration, peak detector and clamp circuit look similar, with the difference that in a peak detector circuit, the output is taken at two terminals of the capacitor. However, for a clamp circuit, the output is taken at two terminals of the diode. We saw that in a peak detector circuit, the output is going to be equal to the peak value of input signal. In a clamp circuit, the output is going to be equal to the input signal, but with some DC shift. So in this clamp circuit, we are going to assume that the voltage across the capacitor initially is equal to 0. This green graph shows the voltage across the capacitor VC. So initially VC is equal to 0. There is no current flowing in the circuit. As a result, the diode is off. And I know that VD is equal to negative VC plus VI because VC is equal to 0. As a result, VD, which I show with this red graph, is equal to VI. So when the diode is off, initially it is off, VD is equal to VI. Then VI reaches VD0 volts. At that time point, the diode is going to turn on and the voltage across the capacitor is going to increase. When the diode is on, V out or VD is going to be a constant value equal to VD0, which is this range, and the voltage across the capacitor is going to increase. And when VI reached its peak value, after that time point, the voltage across the diode is going to be less than VD0. Just like what we saw before, the diode is going to turn off. The voltage across the capacitor is going to be at a constant value equal to, here we calculated it, it is equal to Vp minus VD0. This voltage is equal to peak value of Vi minus VD0 volts. Also, when the diode is off, the voltage across the diode is going to be equal to Vi minus Vc. So KVL holds whether the diode is on or off, or whether the capacitor is charging or not charging. So the KVL always holds, and I can write the KVL in this loop. That's going to tell me that Vd is equal to Vi minus Vc. So after the diode turned off and Vi passed its peak value, Vc is a constant DC value equal to V peak minus VD0. As a result, V out is equal to Vi minus that DC value. So this is graph for my V out. V out has a DC shift compared to the Vi value. Next, we are going to consider the case that there is a load connected to the output of a clamp circuit. When the capacitor is charged and Vi value is past its peak value, the diode will turn off. So in that, when the diode is off, the capacitor can discharge through this RL. The time constant of the circuit is going to be equal to C times RL. When this time constant is much greater than the period of the input signal, and the capacitor cannot discharge much when the diode is off, and the output is going to maintain its shape. Or the output is going to be the shifted version of the input signal. However, if the RC time constant is comparable to the period of the input signal, then while the diode is off, the capacitor can discharge through the resistor and the shape of the output voltage is going to change. As you can see in this graph, the time constant for this simulated graph is, here I have RC equal to the period of the input signal. So as you can see, the voltage across the capacitor changes over time. And so after this time point, when the diode turns off, the voltage across the capacitor completely discharges and the output is no longer the shifted version of the input signal. The value of the DC shift that is added to the input signal using a clamp circuit can also be adjusted. And we can do that by adding a DC voltage source in series with the diode. So we already solved this circuit and you saw that the capacitor is going to charge up to peak value of Vi minus voltage drop across the diode VD node, and after VC reached this value, the diode is going to turn off and V out is going to be equal to negative VC, which is a constant value at this point, plus VI. So V out is going to be equal to VI minus this DC value. Now we can change the amount of DC shift by adding a DC source to the in series with the diode, and here in this circuit the capacitor is going to charge up to V peak value minus VD node plus VDC. Then when the capacitor charged up to this value, the diode is going to turn off and V out is going to be equal to negative VC plus VI. Here VC is a constant value, so I have VI minus VC, which is V peak minus VD node minus VDC. So as you can see, the value of the DC shift can be adjusted by adjusting the amplitude of the DC voltage source. We can use a Zener diode instead of the DC voltage source, because when Zener diode is in the Zener region, we can replace it with its constant voltage drop model, and the value of this voltage drop is equal to negative VZ. So this is my VD and VD1, and this is VD2, and here after the capacitor is charged and the diodes are off, V out is going to be equal to negative VC, and this is my VC, negative VC plus VI, and VC is a constant number, so VI minus the voltage across the capacitor is going to be equal to V peak minus VD0 minus VZ Zener. Clamp circuits can also be used to add a positive DC shift to the input signal, and this can be done by reversing the direction of the diode in the previous circuit. The labeling of V out and VC in the below graph belongs to the clamp circuit. Looking at the clamp circuit, the diode is going to be off when the value of VI is greater than negative VD naught. So I need to have VI more negative than negative VD node to be able to turn the diode on, and also I'm going to assume that the initial charge on the capacitor is equal to 0, so VC is initially equal to 0. For these time points, VC is equal to 0, and for these time points, VI is less than negative VD node volts. So the diode is off and VC is equal to 0, so I know that VD is equal to negative VI plus VC, so VD is equal to negative VI. V out is equal to negative VD. From there, I know that V out is equal to plus VI. So when the diode is off, V out and VI are the same. So in this time interval, this is my V out. Now VI goes below negative VD naught volts, so the diode turns on and V out is going to be equal to a constant value. V out is equal to negative VD naught. So V out is equal to negative VD naught. Then also, while VI was between negative VD naught and negative peak value, for these time intervals, for these VI values, the value of the voltage across the capacitor was equal to VC was equal to VI plus VD naught. So VI is a negative value and VD naught is a positive number, so this is my VC. After the VI reached its peak value, the diode is going to turn off. After the diode turned off, VC is going to be at a constant value equal to negative V peak plus VD naught. So this is the graph for VC. I know KVL always holds, so V out is going to be equal to negative VC plus VI, and I know that the diode is off. From there, I know that the voltage across the capacitor is a constant value, so V out is going to be equal to negative V peak plus VD0 plus VI. So V out is going to be equal to VI plus V peak minus VD0. So we're adding a positive DC shift to the input signal, and here is the output waveform. The value of the positive shift in a clamp circuit can also be adjusted, and we can do that again by adding a DC source in series with the diode. And in this circuit, VC, let me label this the voltage across the capacitor. So VC is going to be equal to negative V peak plus VDC plus VD0, and V out is going to be equal to VI plus V peak minus VDC minus VD0. So by changing the value of VDC, we can adjust the amplitude of the DC shift. We can use a Zener diode instead of this DC voltage source, and if you do that, the output is going to be shifted by VI plus this voltage, V peak minus V Zener minus VD0. In summary, we looked at both ideal case and practical cases for a peak detector circuit, and you saw that in a practical peak detector circuit, if the time constant of the circuit is much greater than the period of the input signal, then the output waveform is not going to depart from its expected shape. For the case of a clamp circuit, you saw that a clamp circuit can be used to add a DC shift to the input signal, and the amplitude of this DC shift can be adjusted by adding a DC voltage source or a Zener diode to the diode in the circuit. Thank you for watching.